Okay. Francesco Ziparo is a PhD student in Pisa at the Scuola Normale Superiore. He's currently working on the implication of considering a fraction of dark matter composed of primordial black holes. And he's working with Simona Gallerani and Andrea Ferrano. And today he's going to give us a talk about primordial black holes as supermassive black hole seeds. It is yours.
Thank you, but I have some technical issues here. Give me a sec. I don't know how to pause this. Okay.
Exit, escape. Oh, your escape is not working.
No, I just got it, and yeah.
Then restart it.
Sure. Let me go back. I'm still sharing, right? Okay, looks good. So again, thank you for having me. I'm Francesco Ziparo, currently working for my last year of PhD at Scuola Normale. And today I will tell you about my recent work, primordial black holes as supermassive black hole seeds. So let me start from the motivation that brought us to consider this work, right? What I'm showing here in this plot is the mass of the black hole as a function of redshift, and those big dots represent the typical supermassive black holes observed at redshift 6 with a mass of 10 to the 9 solar masses, but we also have some of the latest JWST observation. Keep in mind, this is just representative. We have huge uncertainties on the masses of those objects, but for the purpose of this talk, I will use them with those dots. While the continuous line represents the mass assembly of those objects, well, if we assume a standard Eddington accretion rate, right? So you know the accretion rate of a black hole is limited by the Eddington limit, and if you consider this limit, you have this growth for those masses. So we now have a problem, right? Because we don't really know how such massive objects formed so early in the universe. So redshift 6 is around 1 giga-year of the lifetime of the universe, so let alone redshift 10. We tried to answer this question with a few models. The first one are stellar remnants. Stellar remnants are basically black holes that form very early from the collapse of POP3 stars, right? But in order for them to grow into supermassive black holes, namely 10 to the 9 solar masses at redshift 6, a fraction of them has to undergo Eddington accretion for the entire lifetime of the black hole, which you know is a bit different, is a bit difficult because we have radiation feedback for the black hole. Moreover, we have nuclear star cluster. So the appearances of, let's say, seeds, light seeds, with masses around 10 to the 3 solar in nuclear star cluster is governed by the process that goes this way. Very dense cluster of stars forms at the center of the galaxies. A fraction of those stars collapse into a black hole and sink into a core. And eventually this core will go into a runaway process, forming a seed. You know, the difficult point in this case is that you need to have very high density of stars. And again, you have to undergo continuously Eddington, you continuously have to accrete at Eddington rate to get this kind of masses. Finally, we have the most promising scenario, the one called direct collapse black holes, or massive seeds with masses around 10 to the 4, 10 to the 5, maybe 10 to the 6, spanning at redshift from redshift 10 up to redshift 20, maybe. So even in this case, you have some kind of difficulties because direct collapse black holes form through the collapse of dense gas in the very center of the galaxy. But in order to achieve for such a massive gas cloud to directly collapse into a black hole, you kind of need very specific conditions. So even in this optimistic scenario, it appears that the tension between the latest JWST observation and this scenario remains. So what else is left there to try? Before going into that, I want to tell you about the main topic of my PhD research, which is primordial black holes. So, primordial black holes are black holes that form in the very early universe, namely in the first second of the lifetime of the universe, due to the collapse of overdense region. What do I mean? What I mean is that during inflation, quantum fluctuation gets stretched at a super horizon scales. And when those fluctuations re-enters the particle horizon, if they're dense enough, they will stop expanding and collapse into a compact object. So, due to the early formation and their abundances, it might be that primordial black holes are also dark matter candidates. And I will assume they're distributed as dark matter during this talk. So here is a standard thermal history of the universe picture. But in this framework, I want to pinpoint some crucial moments for the life of primordial black holes as well. So as I was saying, they form very early. And some point, since they are dark matter, they will start collapse into virialized structure, and they will form them. And eventually, when you have dense gas into those structure, they will start to accrete and give feedback. So as you can see, there are a variety of scales involved in a vision of, let's say, lambda CDM plus primordial black hole universe. So the first one is a cosmological scale, again, because they form very early and they will impact the growth of the universe through its entire lifetime. There is a galactic scale, of course, because they also impact the structure formation. But what I will focus in this work is a subgalactic scale. So what happens in the very center of the galaxies? Finally, since they impact the universe with several effects, what we tried to do was to try to measure their abundance, right? So what I'm showing here in this plot is the mass on the x-axis and the abundance of primordial black holes on the y-axis. The abundance of primordial black holes in terms of dark matter. So what is the fraction of dark matter which is composed of primordial black holes? And the shaded colored region are excluded. So this is basically an exclusion plot. But as you can see, there are few windows where they can still substantially contribute to the dark matter, right? In this work, I will focus on window C, in particular, on 30 solar masses primordial black holes, and I will assume a monochromatic mass spectrum for those objects, which is a pretty standard assumption in this kind of frameworks. So, the answer that we asked ourselves was, can primordial black holes generate the seeds of supermassive black holes? And if yes, how? Here's how. At least here's a cartoon. I think I love cartoons. I think they help us visualize some processes. And I'll try to describe and break down the process that could bring PBHs to form supermassive black hole seeds. And after breaking it down into three phases, I will try to discuss these three phases with you. The first one is halocrossing. Halocrossing what? You may ask, I'll tell you in a bit. But the point is, we are trying to identify as initial condition the moment at which the gas is able to cool inside dark matter halos. If you have dense gas and a population of black holes in the center of this halo, the interaction between gas and black holes might bring them to lose angular momentum due to dynamical friction on the gas and gather in a central zone of the halo. This has a typical timescale of hundreds of mega-year, but we will see that in detail. If the region in which they cluster is dense enough, they will start forming binaries. And if the escape velocity of this region is high enough to retain the black hole merger products of those binaries, this will evolve into a seed through a runaway process. So let me start from the halo crossing. So what I'm showing here on the left is just a very naive picture of a dark matter halo, where the dark matter is composed of primordial black holes, and we have some virial gas which is sitting in hydrostatic equilibrium with the dark matter at the virial temperature, right? What I'm showing on the other end here on the right is a halo mass growth as a function of redshift for different halo masses. So this is computed just with this Fourier equation 2010. It's a fit from cosmological simulation, and it includes the halo growth through accretion, minor mergers, and major mergers. So at some point, when the halo gets dense enough to cross the atomic cooling threshold, gas is finally able to cool. Why is that? Because at very high redshift, the gas is mainly composed of atomic hydrogen, and as you may know, the Cooling curve of the atomic cooling hydrogen has a sharp drop below 10 to the 4 Kelvin. So here's why we assume that the denser component has a temperature floor of 10 to the 4 Kelvin. So if we are able to reach these initial conditions, dynamical friction might start to play a role in the evolution of the orbit of primordial black holes. So how does the core form? Through dynamical friction. So this is the equation that governs dynamical friction or the orbit decay of the black holes. And as you can see, this also depends on the black hole mass, right? So we also have to take into account the evolution of the black hole mass. And to do that, we are just assuming a standard Bondi-Lyttelton accretion rate computed as a function of the radius of the black hole. So here on the right, I'm showing the dark matter density profile as a function of the radius. I first want you to focus on this black curve, which is the Navarro-Franken-White profile for the halo. But as you can see, if the dark matter is composed of primordial black holes and there is dense gas in the center of the halo, dynamical friction will start to bring PVHs into the center, kind of forming a wave of black holes approaching the center of the halo. And as you can see, there is a huge enhancement of the density in the very central zone. So a good question at this point could be, okay, you have this density enhancement, but when is the black hole core dense enough to evolve in a runaway process? So here is how we define the condition of this runaway process. So here I'm just showing the equation for the escape velocity as a function of the radius, and as you can see, also as a function of the number of primordial black holes. So we can define a critical number of primordial black holes as a function of radius, for which the zone, the region that we are describing, has a escape velocity of 1,000 kilometers per second. Why is this number important? Because this is a order of magnitude estimation of the maximum recoil kick velocity. So if you have that escape velocity, you will start retaining the black hole merger product, right? Here on the right, again, I'm showing a cumulative number of primordial black holes as a function of the radius. So it's just the dark matter density profile integrated over the radius. As you can see, when time passes, this density evolves, and we have a spike in the center. And as you can see, we are also able to define this critical number of primordial black holes as a function of the radius. Eventually, when this evolution will bring us to the point that this critical number is reached at some radius. So that defines the core radius and the number of primordial black holes that is in that radius. So once we get to that point, and the core is able to retain PBH mergers, finally it will collapse in this runaway process. So what I'm showing here on the right is again evolution of the halo mass with redshift, and from the moment, as you can see, from the moment at which the mass crosses the atomic cooling threshold, we need to wait for dynamical friction to bring PBH close to the center, but at some point the cluster will form, right? And this is represented with the dots in this plot. As you can see on the right, on the left or your right, so okay. Those are the typical core properties. So we kind of have 1,000 primordial black holes with 100 solar mass in the very center, so 10 to the minus 3 parsec. And if you compute the core collapse time of that region is extremely small. So it's around 1 kilo a year. So for that reason, we're basically also approximating the moment at which the core form with the appearances of PBH seed. So you have a relation between the halo mass and the moment at which the seeds form. So how are those seeds doing with respect to the observed supermassive black holes? So here are the 5 seeds that I was showing in the previous plot. And this plot is basically telling us one thing. The first thing that is telling us is that if those dots are above this Eddington-like growth of the black hole, they basically can grow into a seed without invoking super Eddington accretion or continuous Eddington accretion. Moreover, a natural prediction from our model is, as you were seeing, is the halo in which those seeds form. So if somehow we can estimate the mass of the halo hosting those observed supermassive black holes, we can also connect each black hole to its progenitor, right? So the estimate that we are doing is very naive. So we're basically inverting, we're using the stellar mass, and we are inverting that relation to get to the halo mass, right? But doing that, we can connect the dots, basically, and we can connect each observation with its progenitor. And even in this case, here I'm showing the mean accretion rate through, sure, okay. Here I'm showing the mean accretion rate through the history of the black hole. And as you can see, even in this case, this is always sub-Eddington, right? So we kind of are able to reproduce this observation with this seeding mechanism. Moreover, a final prediction from this model is the halo, as I was saying, the halo that is hosting seed and the mass of the seed. So first, let me focus on this plot. And again, if you fit the dot, you can have a functional form that is describing the mass of the halo, which is producing a PBH seed as a function of redshift. So basically, if the halo mass that you're looking at is above this threshold mass, those halo that you're trying to look at has already produced a seed at earlier epochs. But while on the other hand, if you're looking at a mass smaller than this one, it may produce a seed at later epochs. And this is just obtained by fitting the colored dots. Same thing goes for the mass of these PBH seeds. As you can see, this is always around 10 to the 5 solar masses with a small drop at higher redshift, but this basically does not evolve much with redshift. So ultimately, this can be used as a seeding prescription for cosmological simulation or semi-analytic models. And here I leave you with my conclusion, and thank you for your attention, and I'll be happy to take any question.
Okay, questions?
So these primordial black holes, they are not very frequent, and finding, for example, UAC1, this is like one Chandra pointing. So what is the likelihood that we are going to find a primary black hole like this in the volume, whatever one Chandra pointing covers?
So again, you can have an estimation of this just by the use of the halo mass, right? So this likelihood to find a black hole seed, let's say, in a volume like Chandra, it's just given by the volume that the number density of those objects over the volume, right? Another thing I would say is that can we detect them? Because like this are you referring to UHZ1, right? So in the case of UHZ1, as you can see, this has I mean, this is a mean accretion rate, but I would say we might have a bias in terms of what we're seeing, in the sense that it might be that we're seeing a spike in the accretion rates, right? But in principle, no, could be, right? But in principle, yeah, the order zero order of magnitude estimation for the number of objects that we should see in that region is just given by the Halo mass function.
Any other questions?
Hi, very nice talk. In the scenario that you were describing, after the core collapse time,
Yes.
is the seed of 10 to the 5 or so supposed to form exactly at the center of the arrow?
Yes.
Or, okay, so it cannot oscillate around. Because that would give also like a periodicity in the actual accretion rate.
Okay, if it form exactly at the center of the halo, I don't know. The idea is that the concentration, the dark matter density that we're trying to enhance, let me use this term, is maximized at the center of the halo, right? And also the concentration is maximized at the center of the halo. So what we expect is that if this happens, it has to happen in the central zone, because you don't have as much PBHs that can cluster at larger radii.
You mentioned at the beginning that you, like most other people working in this, are just assuming a single distribution of PBH masses.
Yeah.
A delta function. Obviously, most phenomena in the universe are powerful. Do you have any? I've not ever seen, and this may not be a fair question. I've never seen a justification for this other than essentially convenience. Is there a reason to believe that it might be a delta function or an error Gaussian, or or if not, how would this all change if you had to have a?
Okay, that's like, for me, the answer is no. There is no justification. It's just a way to compute things, a very naive way, because we don't really know what is the mass distribution for PBHs. On the other hand, what would change if we have an extended mass distribution? It really depends on how PBHs are distributed inside the halo. Because if you have the most heavy objects in the center, then dynamical friction will still impact them, right? So if you have a tail of 10, 30 solar masses PBHs, and with even bigger object that is sitting in the center, the picture would not change. Moreover, if you have a different distribution, the recoil kicks would not be maximized, because the mass of the object, you basically have a stronger kick if the mass of the binary of the two objects in the binary is the same. On the other hand, if they are randomly distributed and you have very light object in the center, the picture might change, because you would need much more time to accumulate the massive one into the center of the edge.
Okay. Any final question? If not, let's thanks our speaker again. Introduce the next speaker while we do a quick, hopefully, change of the laptop. Our next speaker will be Silvano Molendi. Silvano is a senior scientist at the INAF Ziparo. He worked on instrument calibration on several missions, including ROSAT, POSAX, and XMM, and he's also involved in the New Alpina mission. He works on galaxy clusters, mostly on the thermodynamic and chemical properties of intercluster meters. And today, as soon as we can plug everything in, will give us a talk with the title Metal Enrichment, the Apex Accretor Perspective.
Let's see. Can you hear us?
Yes, can you hear me?
One,
Set the audio as the meeting hall, the speaker.
one moment.
Okay, try again. Do you want to try sharing your screen?
Sure. Okay. Okay, let's see if I can. So are you getting that? Yeah, looks like it. Going full screen now. Can you see it?
Looks fine.
Yep, that looks great.
That's perfect.
Okay, so ready whenever you are.
Yep. Yep, go ahead.
Okay, so hello everyone. Oh, let me just get one thing. Yeah, sorry. I wish I could have been there in person, but it is a rather long way from Milan to Boston. Maybe some other time. So today I'll be talking about some work that we've been doing here in Milan. The work is based on a paper that has just come out a couple of weeks ago on the archives. That should be in press, whatever that means these days, in a month or two. All right. So the goal of the project is to provide a coherent and comprehensive explanation for many of the properties of groups and clusters that relate to metals. In doing this, we also gain some understanding of the metal content of other key elements in the hierarchical structure of the universe.
Silvano, excuse me for interrupting. Can you try to speak a little bit closer to the microphone?
I have, this is the microphone, so if you can't hear, it's in the earphones. So if you, unless it's the wrong one, so let me just check. Okay, which microphone am I using?
So online, it sounds fine.
Okay, so Bill says he can hear fine. Yeah, I'm using the microphone that's in here, so I can either eat this or you have to find.
Should be fine. Should be fine. Thanks.
Can I resume?
Yes, please. Thanks.
Right. So so these are the main findings from this work. As far as clusters are concerned, the bulk of the metals is in the ICM, not in the stars. The small scatter in metal abundance that we see arises from the averaging of hundreds of independent enrichment events. The lack of redshift evolution in cluster outskirt abundance is explained by the self-similarity of star formation over a broad redshift range. We also provide an explanation for the iron abundance versus entropy anticorrelation, the flat abundance profile in the outskirts, the lack of an abundance ratio difference between core and circumcore regions, and last but not least, the so-called iron conundrum. Regarding the large-scale structure, what we find is that the gas not bound to halos must have a metal abundance which is similar to that of the ICM. We also find that less than a third of the iron in the universe is locked in stars, a comparable, somewhat smaller amount in gas in groups and clusters, and the bulk, 3/5 roughly, is in a tenuous, warm, hot gaseous medium in or between galaxies. Now, in the 20 or so minutes I have, actually probably 19 or 18 at this point, I really don't have the time to go through all of this, so I'll be picking some of these points and we'll be discussing them. So if we want to make a connection between the iron in the ICM and the stars that produce the iron, we need to find something to do it. And then here we use this quantity, which is called the iron yield. It's defined as the ratio between the total iron mass and the gas mass that went into the stars that produced the iron. Now, as we all know, stars lose mass throughout their lives through various mechanisms. So this m star 0 is related to the m star to that we measure today through some factor. We also make use of the fact that you can write the mass in iron in stars and in the ICM as a product of the metallicity times the mass of the stars or the mass of the ICM. You do so, and you can rewrite this in a somewhat different form, writing the metallicity as a function of other terms, where the other terms are the baryon fraction, Fp, F star, which is the stellar mass fraction, and the F gas, which is the gas fraction. And since we're looking at massive systems, we can assume, at least the first order, that the baryon fraction is just the sum of the gas fraction plus the stellar mass fraction. Right. So the point I wish to stress here is that there is this relationship between the metallicity we measure in the ICM and the stellar mass fraction. And of course, there is then this other quantity which we can think of as a sort of a conversion factor between the first and the second quantity. So what you can then do is you can take measurements of the metallicity and of the stellar mass fraction, put them together, and come up with an estimate of this so-called conversion factor. And this is what is shown in this plot here, where I have the metallicity on the y-axis, F star on the x-axis, and by putting them together, you get some constraints on this quantity. As it turns out, in this case, it's somewhere between, say, 4 or 6 in these units. Now, what you can then do is you can, it's very easy to show that the ratio of the iron locked in stars to the total iron can be re-expressed in this form. And from the constraints I just showed you and having some assumptions on what the metallicity of stars is, you can put all this together and you can then come up with an estimate of the fraction of iron which is locked in stars. And you come up with a number which is somewhere between a 1/7 and a 1/4 of the total iron available. So the take-home message here is that in clusters, the bulk of the metals is in the hot gas. It's not in the stars that produce them. The stars, of course, produce the iron, but then it's released, goes somewhere else. Okay, so what happens when you go to lower mass systems? As some of you probably know, less massive halos feature smaller gas fractions than more massive ones. So if you picture a smaller halo going from the group to the cluster scale, in order to reach a larger F gas, what they have to do is they have to accrete substantial amounts of unbound gas that is not bound to any specific halo. What has always intrigued me is that in doing so, the metallicity of these systems essentially doesn't change. This we know from observations, and this is shown in the plot here. This is work from Simona Guizzardi and Lorenzo Lovisari from a few years ago. So you see on the cluster scale, we have this metallicity in gray, and from the group scale, we have this other metallicity estimate. And by and large, given the uncertainties we have, they are essentially consistent with one another. Now, this fact can then be used to place constraints on the abundance of the unbound gas. How is that done? Well, we consider two different options. The first option is we assume that the unbound gas is pristine. There are no metals in it. The second option is we assume that the unbound gas has the same metallicity as the ICM. Then we build a simple model of the metallicity of the gas. We call it gas rather than ICM because it also includes less massive halos as a function of halo mass. I won't go into the details of this. If you're interested, you can look it up in the paper. And so let's look at what the model finds. And this is the first case where we assume that the metallicity of the unbound gas is 0, it's pristine. I should point out that the model reproduces the metallicity of massive halos by construction, so no big surprise there. What is interesting, however, is what happens when you start off from smaller and go to higher masses. What you see is that you have a reduction of the metallicity, which which is very easy to understand because what you're doing is you are accreting gas which has no metals. So what happens to the metallicity of the halo is that you're actually diluting the metals, and so the metallicity goes down. And as you can well imagine, the situation is quite different when you accrete gas which has essentially the same metallicity of the gas which is already in the halo, and what that produces is essentially a stable metal abundance as a function of halo mass. So what we can say from this is that we can exclude the case of pristine gas, as this would lead, as I just pointed out, to a substantial reduction in iron abundance when going from the group to the cluster scale. Now, what this is telling us is that the unbound gas, at least some part of it, must have been first accreted and later re-ejected with metals in it. As far as I know, this is the first time we have, albeit indirect, still evidence for this. If you play the game I just showed you in a little more detail, you can actually get some estimate of the metallicity of this unbound gas, which is shown here. It's not very strongly constrained, but still I thought it might be worth showing it. Okay, so mass is one dimension over which you can explore metal enrichment. Another one, of course, is time. And this is what is being shown here. What is being shown here in the two plots on the right is the metallicity of systems at different redshifts. There have been several papers in the literature dealing with this argument, and by and large, they all come up with the same result, which is that they are all consistent with no evolution of metal abundance in core excised clusters, which is, again, quite an interesting result, because this is telling us is that the enrichment process of massive halos today must have been very similar to the one which has taken place at a time when the age of the universe was roughly half of what it is today. Now, we discussed this at some length in the paper. I don't have the time to go through it now. There is one point I want to mention, however. If I go back to the relationship which I told you, which is valid for massive systems, because we have we don't account for missing gas here, you see that there is this linearity, essential linearity between the metallicity and the stellar mass fraction. So I just told you that the metallicity doesn't vary with redshift. So if this equation holds, then we should expect that also the stellar mass fraction should not vary as a function of redshift. So we went back and dug into the literature, and this is what is actually measured. So there is a confirmation of this very simple relationship can be found in the literature. Okay, so so much for clusters. Let's see if what we learn from clusters can now help us learn something else about other structures in the universe. So the first point I wish to make is that there are good reasons to assume that this quantity, which is essentially a renormalized yield derived from clusters, applies to other environments as well. And the way I wish to do that is by showing you this plot. This is a plot by Coupon and collaborators from almost a decade ago. And what they're showing here is the stellar mass fraction as a function of halo mass. So if you look at the low mass end, what you see here is that the stellar production reaches its peak around 10 to the 12 solar masses. I should point out that this has been shown in a number of papers, not just this one, and that what has also been shown is that this result varies relatively little with redshift, although this is measured locally in this case. When you go up in halo mass, what you see is that the efficiency with which you produce stars goes down. However, at the same time, if you are a halo which increases in size, as you start going up to 10 to the 13 and 10 to the 14 solar masses, you have a lot of stuff which is falling on it from outside. So by the time so that you are accreting a substantial amount of stellar material which has been synthesized outside the halo itself. So by the time you reach massive halos, clusters, say 10 to the 15, essentially more than 90% of the stellar mass you have in clusters has not been synthesized in the cluster itself, but in some other halo and then accreted. So what this is telling us is that this quantity, this yield I have here, which we measure in clusters, actually describes the iron production in less massive systems, because essentially no iron is produced in clusters. Okay, so that was a long explanation. So I thought I'd have something of a. So this is a somewhat less orthodox representation of the same process. So what you have here on the right is your apex accretor, massive cluster, if you like, which is accreting structures of different size, of course. And as you see, the size scales with the color, and of course, the color represents the metallicity. The smaller systems are also the more metal rich, and you can sort of guess that the color of the accretor is some kind of average of the color of the accreted. Okay, let's go back to being serious now. And so, okay, so you have this quantity. We have this quantity which we think is representative not of just what of the yield, this yield which is representative of processes which do not occur in clusters. And could this quantity somehow be biased? Could there be, for example, an environmental bias? This seems unlikely because the subhalo mass function in massive systems is actually very similar to the halo mass function. So in clusters, we are sampling a distribution of halos, which is similar to the one which is subhalos, which is similar to the distribution of halos in the universe. Could we have a cosmic time bias? The clusters we observe today encode star formation that occurred sometime in the past. So could this quantity depend upon cosmic time? And well, the first answer is I've just shown you that the metallicity of clusters of redshift 1 and today, as far as we know, is the same. So that speaks against that. There are other arguments. However, let me skip to the end of this. The point I wish to make here is that there are estimates of metal production efficiency which are based on entirely different considerations on nucleosynthesis models, which are therefore independent of ours, and they come up with values which are very much consistent with the ones that we come up with here. So let's assume that we can assume that this yield applies to other less dense environments. Then if you can assume that, then it's fairly straightforward to compute, for example, the metallicity of the universe. What you do, you have the metallicity of a given halo, and all you have to do is you have to average this out over the halo mass function, and this is what is shown here. So this is the metallicity of your halo, and this is the averaging out over the halo mass function, which of course needs to be multiplied by the halo mass itself. Now, where is the trick? The trick is here in the second equation, where what you're doing is essentially you're relating the stellar mass fraction of the halo with the metallicity of the given halo using a quantity which is not halo dependent, which is what I've been arguing about over the last 5 minutes or so. So at the end of the day, if you do that, then the metallicity of the universe is nothing more than the stellar mass fraction multiplied by the yield, which I thought so much about. And if you go through the exercise, oops, this is what you get. So the metallicity of all the baryons in the universe, average over all the baryons in the universe, should be, well, it's not particularly well constrained, but it's somewhere between 1/3 and 2/3. Say, I should point out that this is not what you find in previous estimates. Previous estimates typically come up with numbers which are a factor of several short of this one, and so this is one important difference. You can also come up with a method. You can also perform a method budget for the universe. So you can assign.
Silvano, you have a couple of minutes to wrap up.
Yeah, I'm wrapping up. So what you find is that roughly 1/3 of the metals are in stars, similar, more or less, in clusters and groups, and the bulk of the metals is actually in a warm hot gas in or between galaxies. Again, this is not consistent with what you find in the literature. Okay, just a couple of minutes for the implication. So we have we know that the detection of the warm, hot, low density baryons in X-rays is based on metal lines. Now, as some of you, I'm sure, are aware, the detection of these lines has been controversial. One might infer that the lines have not been observed because there are no metals. So this work has something to say about that, because if we have indeed this warm, hot gas with the metallicity of roughly 1/2, the lines really have to be there, but it works both ways, because if and when we will finally have line detections, that this, of course, will also provide strong direct confirmation of the model that I've just described. And the last comment, something similar, but not quite. The fact, according to this model, the bulk of the metals in the universe are in warm, hot gas. And the only way you can access that gas is through high resolution X-ray spectroscopy. So, and of course, the higher the resolution, the better. So let me wrap it up with just one last slide. Here it is. You are essentially what you accrete. This is what you learn from the metals. And yeah, the serious one is this one, but I'm done. Ready for questions, if any.
Thanks, Silvano. Okay, any question for Silvano? Come on, let's not be shy.
Hi, this is Pepe Fabiano.
Hi,
Nice. Hi, Silvano. I agree with you that to really get the metallicity right and you see which under you need the high resolution. You need high spectral resolution, but you also need high spatial resolution if you don't want. I mean, if you have very high spectral resolution, I guess you can probably solve the problem. So, are you thinking here of grating instruments or calorimeters when you talk of high resolution from an observational point of view?
Well, first of all, I'm not really an expert on that specific science, so I just wanted to point to the connection between the work that we've done here. And for what it's worth, my opinion is that a combination of very high spectral resolution with at least moderate spatial resolution is probably the best option. Of course, if you can, the spectral resolution is the key, but spatial resolution would also help. So microcalorimeters, I would say, is probably better than grating.
So it seems like we really need Athena.
Well, I've heard of this instrument that you're building over there, but I hope to build, which is, what is it called, LEM? I think that might have something to say as well, right?
The audience is giggling. Okay, any other question? If not, let's thank our speaker again.
Maybe in chat.
I think the chat is the old.
There's one question.
Yeah, exactly. Okay, let's thank our speaker again.
Okay, bye.
Bye.